Okay, we're doing related rates in this video. This is sort of like optimization, but with some calculus and implicit differentiation thrown in there. It's a very difficult topic, but you'll get the hang of it after doing some examples. Okay, so we've got a ladder up against a wall. So I'm just going to draw this ladder in, and I'm going to draw 15 meters. So it's resting against the wall. Whenever I do a related rates problem, I really like to cross out any information I've already used. So we've got the 15 meters there. We've used that. The bottom is initially 10 meters away. So I'm going to call this length here X, and I'm going to call this length here Y, understandably width and height. And essentially, I've got that X at a time of t equals 0 is 10 meters away from the wall. So it's not always 10 meters away because this ladder is moving, but it starts 10 meters away. Now that I've used up that information, I'm actually going to cross it out. And it's being pushed towards the wall at a rate of 1/4, or in other words, 0.25 meters per second. So pretty much what that means is this ladder is getting pushed there. And you can think dx to t. So how is x changing? That is dx over dt. It's like a speed in the x direction. This is 0.25 meters per second. Now, it's actually not, because it's negative 0.25. Because x was 10, that's going to be getting smaller because the ladder is getting closer to the wall. So that's why there's a negative sign on dx to t. And similarly, I'm just going to cross out that bit of information. How fast is the ladder moving up? So how fast, that'll be something over dt. And is it moving up? So that'll be dy. So essentially what this whole question is asking is dy over dt equals something when x is, when t is 12 seconds. Time is 12 seconds. And that's what we got to find. So we've got some equations to connect it. Normally you'll use equations like Pythagoras, for example. X squared plus y squared is the length squared. That was the length. And pretty much you can replace the length with 15 right away because we got that. So x squared plus y squared is 15 squared, and this is Pythagoras. You probably don't need that first line, but I'm just trying to do it for completeness here. Okay, 15 squared is 225. Let me make sure I've actually got that right. 15 squared, yep, and that's x squared plus y squared. Now you are going to be very tempted to sub in 10 for x. Do not do that. X is 10 at the start, but it doesn't stay as 10. Okay, now we've got the implicit differentiation step. So what we do here is we differentiate everything with respect to time. Now it's not always time in related rates, but it almost always just is. So the derivative of x squared is 2x times dx over dt. You've got to be really careful with that implicit differentiation stuff. Then we get 2y times dy dt equals, and the derivative of 225 is 0. So I might make a little note here, differentiate with respect to t on both sides. Okay. Now, we've got usually 3 out of 4 of these things. So remember, we were after dy dt. And let's see if we can get that. So the ladder is being pushed towards the wall at a rate of 1/4 meter per second. So we're trying to sub in t equals 12 seconds after we're pushing. So we don't know what x and y are, but we can figure them out. So maybe at t equals 0, we've got x being 10, and y would be root of 15 squared, take 10 squared. So that's just from Pythagoras, whatever that is. And then each second, x decreases by 0.25. So now we can look at t equals 12, and then we can figure out what x is. So if it's 1/4 of a second at a quarter of a meter decreasing every second, that means that x has decreased by 3 meters. So x is 7. And where that came from was 10 take 12 times a quarter. Okay. If x is 7, y is going to be root of 15 squared take 7 squared. And we can figure out what that is. 15 squared and 7 squared. And we'll just take the square root of that. Well, actually, I might just keep it as root 176. Okay. And then we can plug in everything. So at t equals 12, we've got 2x. So this is 2 lots of, x was 7. The x to t was minus 0.25 plus 2 lots of y was, I think, root 176. So we'll just pop that in. And we're going to times it by dy dt, and then all that should equal 0. So we've just plugged in everything we know, and we should know most of those things. Okay, so we can just figure out what these are in approximates. So 2 times 7 and 0.25, so this will be minus 3.5 plus 2 root 176 dy dt equals 0. Therefore, dy dt, with still the 2 root 176 out the front, is 3.5 in the positive. So dy dt would have to be 3.5 over 2 root 176. So we can work out what that is. 3.5, maybe we'll do it in fraction mode. 3.5 over 2 times root 176. So this is 0.132. Roughly equals 0.132. This will be in meters per second because we've got a dy dt. Yeah, let's just make sure this sort of makes sense. So y would be getting bigger at 0.132, which is around the same sort of scale that x is getting smaller. So that seems like a sensible sort of answer. And that's how we do that question.